Sorry. I Good wrong? Want to see the word? Right here. I like My parents don't want to go down. Yeah, I just need to check this. My parents don't want to go down. I got it. I mean, what do we, for the checkpoint, like I still need to finish my square. No, he just, I'm like really innocent. No, yeah, he finished the pin and the connecting rod. They come out and have those. You haven't done what? Oh,
okay.
Yeah.
Good morning, everyone.
Good
morning. So we'll continue from last time. We were discussing bending stresses. And my plan for the day, I don't have pre-lecture slides because I want to go along with all of you together here. My plan for the day is to do one derivation. This is probably the last derivation for this semester in some sense. And the other derivation before transverse shear stresses, I'm just going to present that to you and we will make use of that in solving problems. Okay? So I want to go through this though. And is my voice too loud for everybody or is it fine? Okay, thank you. Okay, so from last time, I'm going to consider two different situations. Okay, first situation. I have a piece of the beam. One more. I'm going to call this is situation A, this is situation B. In the first situation, I'm applying a bending moment in the positive sense. Okay? Okay, so this is according to the sign convention. I'm taking the beam and then making it look concave upwards. In the second situation, I'm applying the bending moment in the opposite sense. This is against the sign convention. In both the cases, I'm going to assume, for the sake of simplicity, that the cross section of my beam is a rectangle. Okay? It's a cross section. Is a rectangle, and let's say that the axis, first of all, so y-axis vertically up. Okay. For every cross section from now on, we will be locating the centroid. Centroid is something at the center of the cross section, right? Geometric center. So I'm going to call it as capital C. And for this particular cross section, I'm going to assume that the thickness is 2 times T, just for simplicity. Thickness is little t plus T, and then the width is W. And my axis on the beam along the length is the x-axis. And on the cross section, my axis is going to be the y and the z-axis as we discussed last time. And this is the z. Okay? This dotted line, as you see here, is coincident with the center of the cross section in this dotted line here. Now, in the first case, as you look at the bending moment being applied, imagine the beam being wrapped around a large cylinder. So still case A. I have a large cylinder of some arbitrary radius. Imagine the beam being wrapped around this in the following manner. Okay, so this is how we imagined it to be last time. These are dotted lines. Okay, and I'm looking at the following things on the beam. Small segment here. I'm going to call this piece as the piece CC, and little b, and I'm going to draw the dotted line on this piece here as well. Okay, so this corresponds to the dotted line that you see here, and the radius of curvature of the dotted line is capital rho, the Greek letter rho, from the center of the cylinder. And my y coordinate is going to be measured as positive starting from the dotted line and pointing up. Okay? In this case radially, of course. So starting here. This is positive y. Does this make sense to everybody? This is what we discussed last time. The total radius of curvature of the dotted line is rho from the center of this imaginary cylinder. Okay, this corresponds to situation A. If I now look at the pieces on the imaginary cylinder and then on this beam which is wrapped around there, here is what I will see. CC and BB. Okay, these are the length segments after the moment has been applied. So this is after loading. And this is the piece I'm interested in. And we found out the following. We found out that if I try to calculate the strain at any point on the piece CC versus the strain at any point on this line segment BB, the length of CC is smaller than what it was before. The length of BB is larger than what it was before. So the piece CC is now in compression. The line segment BB is in tension. And in between there is going to be a line segment which does not see either compression or tension. And we call that as the neutral fiber. And for all practical purposes, this dotted line is my neutral fiber. Okay, so this is the neutral fiber. CC undergoes a compression. So length reduces after the load has been applied, length of BB increased. And in summary, for any line segment that is at a distance of y from the neutral fiber, the strain we derive was the following. For any line segment, so these are all horizontal line segments that I'm looking at. So at any point on any line segment at a distance y, measured positive coming from the neutral axis or neutral fiber and going up, on the neutral fiber. The strain that we calculated was the following. So epsilon is equal to minus y by rho. Which means that the strain at any point on the line segment CC, so for example, if I choose this point, let's call that as point A, then let's call this as point B. The strain at point A is going to be what? It's going to be y, which is the distance from the neutral fiber, which in this case is going to be equal to the value little t minus t by rho. This is a compressive strain. I'm sorry. Does this make sense to everybody? And if I look at a point capital B, the strain at that point, epsilon B, is going to be minus, watch this. Now, the point B is sitting below the neutral fiber, which means that my distance y is going to be what? It's going to be negative t. Plus t by rho, so this is a tensile strain. At any point on the neutral fiber, no strain. Which means that when y is 0, there is no strain. And the question to you all now is the following. If I were to look at this beam here, okay, if I were to assign some kind of a directionality to these strains, so for example, this is point A, this is point B, this corresponds to point B on there, this corresponds to the point A on there. What is the direction of the strain at point A and B? Is it along the Z direction? Is it along the Y direction? Is it along the X direction?
Are you looking at the cross section or are you looking at the actual frame?
So this is where I have labeled the point A. So this is point A along the length of the beam. So this is point A. This is point A. I've calculated the strain and I'm saying that it's a compressive strain at point A. Yes, answer.
Would it be like in the X direction, like A would be going inwards and then B would be going like outwards?
Absolutely, it will be in the X direction. So, okay, what is the direction of my bending moment? That is the sense. What's the directionality? So let's choose this guy. What is the direction of this guy? There are two things for a moment, sense and direction. Sense is clockwise or counterclockwise. It has to be accompanied by a direction. Is it into the page or out of the page? Into the page or out of the page, right? So it can be either that or this. The direction of the bending moment in our problems is planar bending moments. These are in-plane bending moments, which means that they will be acting on the plane of the problem, but their direction will be either into or out of the page. Which means that if I look at the cross section, their direction will be directed along the z-axis. Does this make sense to everybody? Okay? So this is called as a planar bending problem, where you take the body on the plane of the body, apply bending moments. Okay? The direction of this is coming out of the page, the direction of this is going into the page, but they are along the z direction. Positive z or negative z, I don't care. So the direction of the strains then at the point A and at the point B, they are going to be along the length of the beam, so they are called longitudinal strains. So bending on the plane of the beam produces longitudinal strains along the length of the beam. Okay? So these are longitudinal strains. I want to write them somewhere here. In this case, based upon the axis system that I've chosen, they are strains along the x-axis. Alright. One more thing I want to do before moving on is I want to look at this situation here. If I had a situation of this nature, how would the figure look like? Anybody? If I were to imagine this beam being wrapped around a huge cylinder, where would you place that beam? Would it be on the top or the bottom? On the top. Right? So if I draw a huge cylinder, center of that cylinder somewhere here. This is now going to be my imaginary cylinder. I'm going to have the neutral fiber. Once again, I'm going to mark the same things as here. So this is B, situation B. This is once again the neutral fiber, the dotted lines. This is, let's say, C, C, B, and B. And if I call this as point A and point B, now let me draw the CC and the BB here. This is my radius rho. Distance y is always measured above the neutral fiber. If I go below the neutral fiber, my y is negative. My question to you is the following. If I look at the point A here, and at the point B, is the strain at the point A going to be tensile or compressive? Is the strain at A going to be tensile or compressive? Tensile, right? Why is that? Is because the length of CC is larger than what it was before. So in this situation, when my bending moment is applied in the opposite sense of my positive sign convention, I'm seeing that the fibers on the top are in tension, the fibers in the bottom are in compression. So these were in tension previously. And these were in compression. Now the tables have changed, are turned. So this is in tension. Compression, which means that if I now write the general expression for my strain, epsilon at any point at distance y from the neutral fiber is going to be plus y by rho. Does this make sense to everybody? If I look at the situation that is described here, okay? If I write the strain at any point at a distance y from the neutral axis, that is going to be plus y divided by rho, which means that the strain at the point A is now going to be plus T by rho, and the strain at B is going to be minus T by rho. They still remain longitudinal strains. There is no change in that particular nature of the strains. So still longitudinal. But I want you to visualize these two hypothetical cylinders. Okay, every time you see a bending problem, look at the way the moments are acting. after you draw the bending moment diagram, you'll figure out if the moments are in the positive sign sense or the negative sign convention sense. And then you picture this hypothetically in your head. If they are in accordance with the positive sign convention, if this is the situation that you have described in your problem, this is the state of affairs in terms of the strains. If not, you go to this one here. Any questions, please? So far. And what I want to do is, you see this row creature, and I'm not really interested in it because that's a hypothetical thing, right? So how am I going to come up with that? So what I want to do, what we would like to do is, from the strains, find out what the stress is, and then what we typically do for every problem, you try to relate the stress to the load applied. You try to relate the stress to the geometry of the problem, so that you're looking at something in an elemental level, and then you're going back to the structural level. Things are happening on the big scale, okay? The moment is acting on the beam in a big scale. I want to find out, okay, what's happening deep down in the point on the body, and then take that idea and expand it into my world view of the moment acting on the entire body itself, okay? All right, so I'm going to erase this portion of the board. And we're going to do the following. I'm going to assume that my material is linear and elastic and isotropic. Linear means strains and stresses are linearly related. Elastic meaning that I am still sitting in the elastic regime of deformation. Isotropic meaning that the material properties do not change with directionality. If that is the case, my stresses and strains are related. If I have longitudinal strains, I'm going to have longitudinal stresses. Do you know of any other stresses that are longitudinal? Yes?
Would it be normal?
Normal stresses or axial stresses. You know, you had these axial problems where you had applied load along the length of the body and you caused some stresses. Those are normal stresses. So the bending stress is also a form of the normal stress, which means in a problem that has both axial loading and bending acting, they will be additive. I can either add or subtract the bending stresses with the normal stresses. So this is also longitudinal. This is a form of the normal stress in bending, but it's caused due to bending. Instead of epsilon, I'm going to substitute minus y by rho. So for m applied, according to sign convention, sigma is E times epsilon, which is minus E times y divided by rho. Quick question, what's the nature of the strain? Is it linear or non-linear? It has to be linear. We're studying linear theory. It has to be linear, but the evolution of strain, that's not necessary. Okay, I can have stresses that are quadratic, but they still are in accordance with the linear theory where the stress and strains are linearly related. This strain is linear because it changes linearly as a function of the distance y. The bending strains that we study are linear strains. Okay, so for us, epsilon minus y by rho is a linear dependence on y. Yes, sir, question.
Does that have to do with the fact that when we're taking the cross section, we're assuming it's a rectangle instead of like a cylinder or something like that?
Not necessarily. Not necessarily. Yeah, it has nothing to do with the geometry. It has everything to do with the way the evolution of the distance takes place. Because you see, how did we do the derivation? We said that if I look at this line segment CC, the length of that line segment was rho minus y times d theta. So that's where the y comes from. Yeah, sure. Looks like my mic is a little too loud. I want to tone it down as you start. Okay. Is this better for everybody? Can still hear me? Okay. Okay. So now what I want to do, I want to do two things. First, I know that the strain is changing linearly, so the stress has to change linearly with distance. Y is always the distance from the neutral fiber, positive above the neutral fiber, below the neutral fiber it is negative. What is the neutral fiber? The fiber where there are no strains, bending strains, which means there are no bending stresses there either. Okay? So this is bending stress. And I want to draw its evolution by looking at, for example, this beam here. How does it look like? How does it evolve? It evolves linearly, we know that. First things first. I'm going to look at a front view of the beam. Okay, so which means that I'm just coming here, staring at it, looking at the front view. After the application of the bending moment, the beam is curved, but the radius of curvature is so large, like I said, the world looks flat, but it is curved indeed. So the radius of curvature is so large that you don't see the curvature when I draw these things. Okay? So here is a flat section. I'm interested in the evolution of the strain, so I look at this piece from CC to BB. If epsilon is the largest on the top and the bottom, as you can very well see, if you have a rectangular cross section, the strain's magnitude is going to be the largest at the top and the bottom, and because they are farthest away from the neutral fibers. The stresses, if they are linearly proportional to strain, also have to be the largest at the top and the bottom. It is just that the sign of the stresses will be negative at the top, positive at the bottom. So if I draw the stress distribution, it's going to look like this. The arrow on the top is going to be the largest of the lot. But it's going to be a compressive stress, so, and you'll see what I'm talking about when I draw a three-dimensional view of this. Compressive meaning that it's trying to take this point and push it in. Tensile being it takes a point and tries to pull it out. So the stress is here. Will be tensile. And these stresses will linearly decrease to 0 at the neutral fiber. And they will linearly increase as you go away from the neutral fiber below.